Hello, in this video I'm going to show you how to use the PlanOpSim software to analyze the performance of a Metalens that we designed from the Meta Component module. We will start by a simple analysis where we only want to visualize the focal spot that we've created in our Metalens. For this I'm using the aspheric lens that I've designed in previous videos. So just to remind you, it's based on the analytical equation for the wavefront of an aspheric lens, designed to focus at 75 microns from our lens. This is the amplitude and phase of the wavefront that we've recreated. We then ran the design, and with that design we can now move on to the Analysis tab. In the Analysis tab, you'll notice that there are three main blocks. One is called Setpoint, here on the left. One is called Sweep Variables on the right, and below there are the far field and near field wavefront parameters. The first thing we want to do when creating an analysis is to define the set point. By default, the set point is the same one as the one for which our lens was designed. The set point controls the incident conditions of light on our meta component. So in this case, we have a meta lens to be simulated with accuracy setting 3x3, having angles 0, so normal incidence, and a wavelength of 0.94 microns, so a little under 1 micrometer wavelength. These sweep variables we will leave aside for a later analysis, because in this first analysis we only want to have a look at a single incident condition. And with that we can move on to the wavefront component here, where we will select which quantities we are interested in looking at. We can either look at the near field, so that is the phase front that we wanted to recreate right after the meta component, or at the far field, the projected intensity at a certain distance away from our meta lens, or we can look at both. For this demonstration, I will select both. We're on the one hand going to look at the wavefront that we recreated and see if it's close to our desired wavefront, but we will also look at a focal spot at the focal distance that we set. So we will keep the spot centered at 0, 0, but at a distance of 75 micrometers, and we'll look in high resolution at the spot itself. So we'll only take a small width and height of our analysis, but we'll increase the resolution to 250 by 250. Voila. This is now all I need to do for this simple analysis. I can just give it a name, so I will call this the spot visualization. Voila. And I can launch the analysis by clicking New Analysis. This will then let the meta component calculation simulate the behavior of the meta lens at different distances and for different incident conditions. Voila, here our analysis is finished and we see the spot. Here on top under Result, you see that we have two plots. One is the far field wavefront, so that's the projected spot at our selected distance. If you recall, that's the one we defined here, so 75 microns away from the meta lens itself. And on the right we have the near field wavefront, which has two components. One is the amplitude, so that's the transmitted amplitude through the lens, and the other one, which we can get here from this drop down, is the phase, so that's the wavefront phase we were trying to recreate. And as you can expect, because we are approximating a continuous phase with a series of discrete meta atoms, there will be some wavefront aberration occurring because of the meta atoms that we've selected. But with this we have done a simple analysis where we can see that yes, we have approximated the wavefront, and we have a focused spot in the location where we expected, in this case 75 microns focal length from the meta component. In the next video, I will show you how to take this analysis further and look, for example, at spectral variations of the focal spot or changes in incident angle. See you next time.